Hi, in this video, we want to take a look at classes for data analysis in R. All right, so in this video, what we're going to do, we're going to take some code from Applied Spatial Data Analysis with R, the textbook, and this is specifically chapter 2, and we're going to run through examples to illuminate and get better understanding of the different classes we have for spatial data analysis. Now, something that's very important about data science is that we need to know what we're working with, what our options are to keep things organized. I feel like this is a feature of education for statistics, data science, data analysis, data engineering that is largely passed over. But this is really a fundamental aspect of data science. It's just knowing what I have and how I can work with it to be able to get the best result possible. If I don't understand what I'm working with, I can't get the best results out of it. All right, so we are working from Applied Spatial Data Analysis with R. This is chapter 2 material, and here is the course or the textbook's website. Now, I'm taking code from the author and I'm modifying it, and specifically, I inserted keywords and I changed the names of objects so that we have like structure, then a descriptive name every single time. And I find that that's a good way to go professionally. The author goes through and lists out all the data sets needed for the examples so that, that way you know what you're going to need to be able to work through everything. That's very nice. I really appreciate that. This data set I was unable to find though. And I'm just going to comment that out and just skip over that portion. The code is included in the video, but I won't be executing it. And here is the information for the book as a citation. All right, so the first thing I do when I get started on a project, I want to make sure that I have a clear workspace, and I want to make sure that I know where I am on my computer. So here, I'm just removing any old objects in my workspace. So don't run this unless you want to lose everything that's on your workspace. Kind of a risky thing. For this project, it's appropriate. And then I always like to set my working directory to where I'm going to be working in my computer. That way I can call things faster and easier and with shorter code. Now, there's kind of a rub to that, is that when you're using R Markdown in RStudio, a recent development is that setting the working directory, you get kicked out of that working directory after you end a code chunk. And so to overcome that, I try to use this to work through, and I feel like I'm getting inconsistent results. All right, so let's go ahead and look at some fundamental operations in R. So of course, first and foremost, R can be used as just a big calculator. And so as a calculator, we can do arithmetic functions, addition, subtraction, multiplication, division. We can put numbers to a power, to an exponent, and we have pi stored to a finite number of decimal places inside R. Now, another way to execute this same thing is I could do this. So here I'm just multiplying pi by 100 to get this number. Another way is to specify in quotations the multiplication, and then what's happening is R is treating this as an operation, as a function. And so we have open parentheses, close parentheses for the multiplication function. Then inside here, I have the things that are getting multiplied together. And here, since I want the exponent evaluate first, I can do exactly the same thing. Now here, order matters in that 10 to the power of 2. Now, and we see we get the same results. And now I can also do this across vectors. I can specify 1 through 10 and then put it to the power of 2, then do my multiplication. And so 1 through 10 to the power of 2 times pi will give me all of these different numbers. So I can, if I have a whole range of values, I could do the operation very quickly. Also, if there's a number I'm going to be using over and over and over, I'm going to use this arrow notation. So it's going to be less than a minus sign. equals an arrow together. Now they have to be immediately adjacent. You can't have a space in between them, and that will define it. And when I do this, I'm telling R to remember to store the outputs. And so later down the road, I can call it anytime I want. In most applications of R, if you just have an object and you just call its name in your code, what will end up happening is it will go ahead and just print that. That doesn't always work out. There's sometimes that doesn't work the way we want to, such as if I'm inside a for loop, I can explicitly print it by going print then that. If I want to control the number of digits inside a print statement, I just say digits equal that many. I think 22 is as far out as we could possibly go. Now, something that is going to be a big deal in this video are object classes. All right, so an object class is basically a stamp that tells R how things are organized inside for an object and what functions I can use on that object. So here, the class of X, which is 100 times pi, that class is numeric. The type of is double. So it's numeric data that is stored as a double. Now, I can also go to a data set. So let's take the cars data set and call its class. Well, that's just a data frame. Also, if I go type of for cars, what is going to get printed is a list. All right, so lists are really the most flexible storage format in R we could possibly get. And data frames under the hood, we don't see it directly, but under the hood, a data frame is always a list. It's a list of vectors that are put together. And so anytime I have a data frame, it's actually a list, but it's an organized list in a very particular manner. And here are the names that we have for cars. We have speed and distance. And if I call summary, we'll get the summary statistics from our data frame. All right, so when I have numeric data in my data frame, we're going to get minimum first quartile, median, mean third quartile, and max. So we're going to get the quartile values for the data, and we're going to get the arithmetic average also. And what this will do, this will print the summary statistics for each column. Now, if I have categorical data stored as a factor, it'll give me a table of the most frequent levels, and if it's a character, it just says character. The structure function is one of the best ways to see what is inside objects in R. So if I have an object, I don't know what it is, I'm not sure what's in there, how it's organized, the str structure function will print that for me. So we can see if I run structure on cars, it's a data frame. I see that I have 50 rows, 2 columns, and those 2 columns are speed and distance. And I can see the first few values just giving me an idea of what's going on. Oh, and also we can see that these are numeric. Now we can also have formula classes. So distance depends on speed. And if I run class on that, R will automatically figure out that it's a formula. And if I want to, I can run a linear model where the first argument is the formula, the second argument is the data, and then LM stands for linear model, and does a quick ordinary least squares model for me. Very nice. Now, the next thing that we can talk about is binning my numeric data. In a lot of applications, it's hard to explain continuous data to people. If you're looking at histograms, people really don't think in that manner in terms of continuous data. Like, we know that there is like a gradient, there's there's kind of like a scale going from, like, let's say short to tall. But when I do data analytics, people really want simpler things to interpret. They want like short, tall, short, medium, tall, maybe very short, short, tall, very tall. They want something easier to understand. They want categories. The cut function goes through and does the categories for us. So here I'm taking the data, I'm specifying the breaks. So how do I want my data organized? And then what's going to happen is that this is going to be, it's going to set up half open intervals. So remember half open from like college algebra intervals. It's going to set that up. And so when we run this, if I had this as false, I would lose my lowest value. And so I don't want to do that in most applications. So you want to put it to true. And we can see that it gets stored as a factor. Now, when you do this, anticipate that it won't be an ordered factor. It won't be ordinal. Now, another thing I can do is I can plot. So here, if I'm interested in the relationship between speed and distance, so it should be a strong relationship, I put the formula, I specify the data, and I go ahead and put a title on there. And here I get a scatter plot, and that looks like there's a linear relationship to me. We can do box plots. Remember, box plots are 5-number summaries of minimum first quartile, median third quartile, and maximum. So here I'm looking at distance, or where I take all the distances and I group them together by that cut function that we looked at a moment ago, and we can definitely see a relationship going on. So you notice that the boxes are shifting upward as you go from left to right. And now here I can also use that categorical data as a predictor variable. And what's going to end up happening is it's going to take averages over the entire subgroup, since I only have one predictor variable. So here's my baseline, which will be, I think, the slowest speed. And to get the average across this one, the average distance across this one, I have to add these two together. And to get the average distance across this one, I have to add the intercept with this. And across this one, I have to add the intercept with this. If you put +0, you won't have to do that intercept adding business. All right, so now let's actually look at spatial objects. All right, the heavy hitter package for this video is the SP package. All right, so this is a fundamental spatial analysis package. This works well with almost every single package in R. So this is, if you're going to be doing spatial data analysis in R, you need to know this package pretty well. Well, I mean, actually, you'll get forced into knowing it, whether you like it or not. All right, so let's go ahead and look at the first two classes. First one is a spatial class. So this is an abstract class for which useful spatial classes are derived. All right, so I'm copying and pasting help documentation here. And the CRS class is the class of coordinate reference system arguments. All right, so what this will do is this will tell R how to perform the projection when I have my data. Remember that the Earth is, not flat. I'm going to represent my data on a flat surface. There's going to be a distortion. This type of class tells R how to handle things going from the round Earth to the flat map. All right, so let's go ahead and take a look at what do we have when we look at a spatial object. Well, when I look at a spatial object, we know that we are going to have a bounding box. We're going to have a projection string. The bounding box is a matrix, and the projection string is a CRS object. All right, and we know that we have subclasses. So there will be spatial points, spatial multipoints, spatial grids, spatial lines, spatial polygons, spatial points data frames, spatial pixels, spatial multipoint data frames, spatial grid data frames, spatial line data frames, spatial pixel data frames, and spatial polygons data frames. And we're going to go over the most important ones in this list. Now let's look at the CRS class. Well, we can see that there's just one slot in there. There's the projection arguments, and it is stored as a character. All right, so let's go ahead and start playing with this a little bit. So let's do a very simple example. Let's go ahead and get a bounding box, which we know is a matrix. So I'm going to go with the most simple numbers possible, 0 and 1. And I'm going to put this into a matrix, 2 rows, 2 columns. And we specify min and max. And then for my CRS objects, I'm just going to put a blank in a character. So remember, the CRS is going to be stored as a character. And I'm just going to put in a missing value as my character, just as a placeholder so we can see what happens. And so here, this is my coordinate reference system of a blank item. And so here is what it's looking like. So now if I want to create a spatial object, I need to specify the bounding box, which is that matrix I just created, and I need the projection for string, the CRS projection. And so here, if I call it, I can see that it's a spatial object. It has a bounding box, as I specified, and I have a projection string. All right, so that's not very useful. That's not very interesting. So let's do it all over again, but with a more coherent example. So now I'm going to have some different values for my bounding box. All right, so now realize that the order of this is 350 is in the upper left-hand corner, 85 is in the lower left, 370 is the upper right, and 95 is lower right. It's going left to right, top to bottom. So one thing that's important is that the entries in the matrix are going like this. So this is being treated as the first column vector. This is the second column vectors. The default is by column vectors. Remember that anytime you're working in R. And that makes more sense from a linear algebra point of view, by the way. That's why we do it that way. And then let's go ahead and specify my spatial object. I specify my bounding box. I specify my projection arguments. And WGS84 is a good default projection for most projects. And so now we can see what we've got going on. We get our bounding box, and I put in my projection. But now, there's a little bit more going on. R knew to go ahead and get all the information about the datum, the ellipsoid, the axis. All these features of the projection are taken care of automatically, easy peasy lemon squeezy. All I have to do is just put in a few letters and I get exactly what I want. So remember that we model the Earth with a collection of ellipsoids that intersect with each other. All right, so now let's talk about spatial points. All right, so the spatial points class is for possibly irregularly spaced points. So this is not a grid. This is points that might be scattered all over. So let's go ahead and get an example to work with. So I'm going to take some data from the author. And it's going to be the Crayon 051001A data set. And I need to specify longitude and latitude. So longitude corresponds to east and west. Latitude tells me my position north and south. And so here I'm just specifying basically the location of everything. I'm specifying the numbers. Now, when I'm working with a spatial points object, we have several slots. We have the coordinates, we have the bounding box, and we have the projection string. The coordinates are stored in a matrix. The bounding box is also a matrix. It's a 2x2 matrix, and the projection string is CRS like we had before. And here are our subclasses: spatial points data frame, spatial pixels, and spatial pixels data frame. Okay, so now let's go ahead and let's say I want to update my projection. So what I want to do now is, all right, I have a projection. I realize it's not the best one for my project. Maybe I need to zoom out. Maybe I need to zoom in for what's going on. Maybe I just picked a bad projection, or maybe I want to just explore different ones. So what I need to do is I'm going to go through. All right, so all I do is just include that inside my projection for string aspect. And I just specify my coordinates, and R will take care of the rest of forming my spatial points object. So to create it, I just go to the SP package and call the spatial points function. And so now if I call summary, if I I'll get some output. If I call the full thing, I'm going to get blasted in the face. I don't want to print the actual object. Most of the time when you're working with spatial data analysis, you don't want to look at what's going on directly, because you're going to have a lot of points, a lot of spatial points. It'll just be too much to look at. You want to look at how it's organized and what's inside each slot. And so here I get my bounding box. When I look at the summary, it's not projected, so there weren't any alterations going on. So something that would happen is I could change the projection and it will figure out the new projection for us. Here is my projection string. And it's got 54 points. If I want to, I can grab the bounding box, and only the bounding box, using the B box, the B box function in the SP package. And so here's the minimum, maximum, and it's just going through the minimum and maximum of the data points I put in. And now here I can grab the projection string, going projection for string in the SP package. And here it is. And it gives us some warnings. And this is because I was building up things manually. Everything's good. Everything's the way I want it. So I don't have to worry about this. Now, if I want to, I can change the projection by changing the projection for string using this arrow notation and a new projection that I'm interested in. So here what I'm doing, I'm wiping out the projection and not replacing it. But if I had a new projection string, R would automatically figure out the adjustment for us. All right, so here I can go ahead and specify the projection that I want to be WGS84, which we defined previously in another code chunk. Now, another thing that I can do is I can specify which points are in the data set that I want. So what I'm doing is I'm taking the data where I originally got latitude and longitude. I'm looking at the data. I see, hey, I'm interested in a specific subset. I'm going to look at just the ones, I want the rows of data that are only for Brazil. And I use a which function to specify which rows those are. Well, we can see rows 4, 5, 6, 7, and 8 have a location of Brazil. And so now if I call only these numbers, so here, this is a vector of the numbers 4, 5, 6, 7, 8, and I specify that, I can get the coordinates. So if for my project I was only interested in those, or maybe I want to color them differently on my map, it's easy peasy lemon squeezy. Now, once I do that subsetting, I retain all the nice features of my spatial points. This is very nice. This is one of the most powerful aspects of R, is that I subset and everything works out the way I want it to. And so now you'll notice that my bounding box, my B box, has changed. It's automatically adjusted. And it says the number of points is only 5. All right, so now let's do another one. Let's say I'm only interested in the points where it's south of the equator. Okay, well, how would I do that? Same thing. But what I'm going to do this time is I'm going to go coordinates. I'm going to say, hey, I want to treat this as coordinates. And then what I'm going to do, I'm going to specify only that second column. All right, so that's going to specify my position north-south, and I want to be in the southern hemisphere, so I'm going to go less than 0. And so the which statement gives me that. So here, this will give me all the rows that are south of the equator. I store it in a vector, and now I can subset this. So like, for example, you'll notice the author put a negative sign there. So here, this is everything that's not south of the equator. So this command figured out all the rows for south of the equator. This says get everything but that because of that little negative sign right there. And so now let's take a look at what happens. All right, and we can see that everything is set up the way we want it to be. Here's our bounding box. And we see our projection hasn't changed. And we can see that our points have reduced. Okay. And remember that the row names by default are just going to be numbers, 1 through number of rows. And this str function displays that. All right, now let's look at spatial points data frame. Now this is where things start getting more interesting. What's going to happen is I'm going to have my spatial points, but I'm also going to have a data frame. And what's going to happen is that each row in my spatial points, each row for my coordinates matches to a row in my data frame. And so what's going to happen is that under the hood, R is going to match them up by row position. And then if I want to start working things from a data science point of view, all right, this tells me the location, this tells me the informative statistics, let's match them up so that I can do my analysis. All right, so if I'm going to do this, if I want to create a spatial points data frame, I just use a spatial points data frame function from the SP package. I specify my coordinates, I specify my data, I specify my projection string, and I say match ID equals true. And so let's go ahead and look at what we get out from this. All right, well, if I call, let's say, just the 4th row, the author just picked 4, is basically just a random one to pick. What's going to happen is that all of these are coming from the data frame port. So these entries came from the data entry, and you'll notice that it includes longitude and latitude because longitude and latitude came from the data frame. But I also have coordinates, which is coming from the coordinates parameter. And if I want, I can take a look at individual aspects. So let's say I'm interested in just the location for my data. Well, if I go $loc, what it's going to do, it's going to call that column from my data frame. And then boom, I can work with it just like any other vector in a data frame. Almost all of the data frame operations we can handle directly, and R will know to work with the data the way we want to. I can also, instead of using $sign notation, I can use parentheses instead. Notice that I've got double brackets going. So things are a little bit different than in regular data frames, but things are in spirit the same. If I want, I can sample my data. So I can use the sample function to randomly select rows from my data frame. And so here, what this is doing, this is actually picking all the rows and permuting their position. So this isn't really that interesting because the data frame stays the same. I haven't subsetted my data. I haven't oversampled my data. It just switches up the location on things. But everything is going to be, it's going to be the same data, same coordinates. They're just going to be in different row positions when I do this. So what happens is this defines a permutation on the rows. This part says, hey, shuffle around the order of my data sets. Match ID, this is going off of the rows for this. The row names are being used as the IDs, and all equal, we can see that the 2 spatial points data frames are in fact the same. It's important that I have match ID equals true. If I didn't have that, I would have coordinates stay the same, but the data frame would be permuted, shuffled up, and things would get screwed up. And so let's take a look at this. So here we can see that row 4 is in Brazil right there. I'm not even going to try to say it. And if I went down here, row 4 is in fact the same. So things are good. Doesn't matter which version I've got. All right, now if I start playing around with the name, so in this example, what happens is that the names are changed. So you'll notice that I've got letters. So the letters vector in R is stored, automatically comes in R, and it's just the letters A through Z. If I go through and I randomly sample the letters twice and then paste them together, I just have a new character string. So what this is doing is that this is creating junk row names on my data frame. And so what happens if I if I try to match up on ID, I'm gonna have problems. There's gonna be an error. So what I've done here is that now my data has junk row names that don't match my coordinate row names. So when I go to match the ID, it's not going to work out. So I'm going to get an error, which is just a little bit off the screen. Oh, it did not print it. Oh, darn it. Oh, phooey. All right, so you'll notice that this is a try statement. And so here, basically, what's happening is that there's an error in the code because R can't match these up. Now, if match ID was equal to false, it would go by position. So first row goes with first row, second row goes to second row, third row goes to third row, and so on. Now let's look a little bit deeper at what we've got. If I use the get class command, we can see that we've got several slots. We have data, coordinates, NRS, coordinates, VBox, and projection for string. And so data is a data frame, coordinates NRS is numeric, coordinates also is matrix, bounding box is a 2x2 matrix, and then the projection for string is a CRS object. And this extends spatial points and spatial and has subclasses. So these are subclasses of spatial data frames. And this has a this is a subclass of these two, and this is a subclass of spatial points data frame. And here's the names of our column. So if I call names on it, it will give me the names from the data set. You'll notice that the coordinates, the explicit coordinates parameter is not being called. And we can create model frames using these. So I can say latitude depends on longitude, and model frame is just modeling frame for linear regression, most of the time linear regression. And here we just see that it's a specified data frame. And I can use spatial points data frame and specify it in this manner also. So I need to specify my coordinates and my data. And once again, I'm going to have everything be equal as long as I'm making sure things match up correctly. And this gives me another way of building things out. I can keep on playing with this. The author is just doing a good job of making sure we can see the different ways that we can work with this and build these objects. And so if I want to look at the structure, I can see that I have a data slot, a coordinates NRS, coordinates, a B box, and projection for string. And so we can see what is inside each slot. Now notice that I have an @ instead of a $sign. If I want to call this explicitly, I need an @ sometimes these can be a little bit harder to get at to directly. We'll want to use a special function, which we'll hit in a moment. And if I want to call the names, this is going to give me the column names of my data sets. And so, so coordinates don't have to be latitude and longitude. There are other ways to specify your location. If I want, I can specify that the coordinates are recorded as longitude and latitude. So it is also possible I could have latitude and longitude switched. I'd like to know that. And so when I do that specification, that's going to get brought into here. So it will be in this attribute down there, and I can specify my projection, which will be stored in here. All right, so let's go ahead and use SP coordinates to get a spatial data frame. All right, so here I'm just going to run through an example. I'm going to take some data of a turtle in the ocean. All right, so here's my data set. I'm going to use CMAP 105 mod, which is from the publisher's website. Here's a summary of the data. So here I've got the ID row, I have latitude, longitude, and the date. So first thing we're going to do, we're going to convert the date to a date format. And so we can see that it's stored in there as month, day, year, and then hour, minute, second. And here is our time zone. Now I'm going to build my data frame, and I'm going to specify. So I'm taking the original data I have, and I'm going to put timestamp in the data frame as the converted time that I have. Now you'll notice that I've got time in here, time and date. I have time and date here, so it's actually redundant, but it's not a big deal, not a problem. And then here, what we're doing, we're specifying latitude and longitude. So if so some of the data is on different sides of the international date line. So to deal with that, if the longitude is less than 0, we're going to add 360 to it. So that way we can see it as a continuous movement. If I didn't do that, it would look like the turtle is going, then all the way going around the planet to just the other side of the international date line, then moving along like that. And so this is just so that we can project things correctly onto the map. And just to make sure I have everything in order, I sorted the columns by the timestamp. I'm going to specify that I'm working in longitude and latitude. I'm going to set up my projection to be the good default of WGS 84. And I'm going to pull in using system file the gshhsc.b in there. And this is for the purpose of plotting the map, by the way. And then I use map tools. RGSHHS is going to take this and convert it to a usable format. I'm going to call it PAC for Pacific Ocean. And we're going to plot the SP slots. I'm going to keep my axes. I'm going to color everything khaki 2. And I'm going to have I as a parameter for x-axis, y-axis. Now on top of that, so this is my map. This is going to be my data points of the movement of the turtle. I'm going to convert things. I'm going to get months for what's going on, just so I know what's. So I'll have the month number, and I'm going to have a cumulative sum, and I put in -1 for baseline aspect. And then I'm going to just have my coordinates in there. And then I put on some text throughout. And let's take a look at the actual map. And so now I can see a progression of where the turtle was as time went on. So September, October, November, December, January, February, March, April, May. Between May and June was kind of like hanging out here. And then July and August. So, that's interesting. All right, so now let's look at lines or lines, and spatial lines classes. So a line class is a class of a line object. I mean, it's not really that exciting, not shocking. Lines, plural, is for a collection of line objects. And then spatial lines are a special class of lines. Now, contour lines are not going to be covered yet. We're getting, just hold your horses, we'll get there. So when I'm talking about an individual line, I have coordinates which are stored in a matrix, and its subclass is polygon. When I talk about lines, we can see that we have lines and we have ID to keep things organized. So this is like my individual line, and this is the ID on it, so things are organized. And for spatial lines, we go a little bit further, that we have a line, and then we have a bounding box, and then we have a projection. And this extends spatial and spatial lines null. And for subclass, we see that we have spatial lines data frame. All right, so let's once again do another example. This time we're going to put down some stuff with Japan. So I'm going to use the maps package, the map function. I'm saying, hey, go into the world database, grab the Japan region, but don't plot it. Go ahead and specify my projection. I'm going to say that I want everything in longitude, latitude, and I'm using WGS 84. And then I'm going to convert that map to spatial lines with map tools. I'm going to take the map of Japan, take the coordinate on there, which is important, because notice I didn't specify the coordinates in Japan. And now I can look at the structure. And we can see that in spatial lines, we have our lines, our bounding box, and our projection. I can figure out the length of stuff. And so we can see that there is one actual line in our lines object, and it's of length 34. Now for contour lines, frequently these are stored in spatial lines data frames. All right, so spatial lines data frame, this class holds data consisting of sets of lines where each set of lines relates to an attribute row in a data frame. Frequently, we're going to use this for elevation. So here I'm going to get the contour to spatial lines data frame function in map tools. I'm going to take the contour lines from the volcano data set, which is a data set in base R. And here I'm going to start using the slot function. The slot function, what this does, this goes in and this finds a particular object inside my object. So it takes an object, finds a slot, and grabs whatever is inside that slot. And all right, so what we're doing here, we're grabbing data. This is a good way to grab objects when you have more complicated structure. And so here we can see when I grab that, I can see the elevation for each contour line, this is probably in meters. Now here, let's go ahead and specify my projection. And now I want to do convert a map to spatial lines. So I'm going to grab the data of Auckland map gen.dat, specify the projection, and I can see that I have an object of spatial lines. Here's my bounding box. It has not done any a manual projection, but I do have the projection stored going on. If I want to look at the slots of lines, I can do that with the slot function. So when I use slot, remember I need to specify the object and then the name. Now let's say that we're interested in particular in some islands on this map. This code here goes through and grabs which ones are the islands. And I decided to store that in a vector and call that the islands vector. And so I can subset that. So this specifies where in my data do I have islands, and I pass that to this, and this will be my spatial lines for islands. So I'm grabbing my spatial lines, subsetting to just the ones that are islands. And now if I want to, I can just look at their lines if I'm interested. Now let's work with spatial polygons. All right, so what this does is this holds polygon topology without attributes. So this says, so this will be something like school districts, counties, countries, two-dimensional regions, not like boundaries. So if I have boundary, that's a line, but if I have a region, that's going to be a polygon. Now, if I have data that I want to connect to individual counties, individual states, this will not be the right class for me. We'll get to that class in a moment. All right, so when I talk about spatial polygons, we're going to have polygons for each individual region. We have a plot order, which is important for telling R how to put them down. So it's possible that we have overlap between our polygons. When I have overlap, depending on how I'm plotting things, I can get a very different image going. Here's my bounding box, and here is my projection specified. And so this code goes through and specifies my spatial polygon from the list of lines I've already grabbed. So the previous code grabbed a whole bunch of lines, and now I'm going through and I'm converting those lines over to polygons so that I can plot them as polygons. And this code just kind of slugs through that. The heavy hitters for this is to go individually and grab the polygon. So I take lines, make it into a polygon, and then I make the collection of polygons into a collection of polygons. And I need to keep things organized for this so that I can always connect back to my data later and get the order of plotting. And so now let's take a look. So here is what I've got. All right, there's my map. Now, if I want, I can take those lines we had a moment ago of the islands, I can fill them in gray, and you can see down here that there's some gray islands. These islands correspond to what I pulled out in that previous chunk when I was doing my subsetting. Pretty nifty. This is pretty slick coding. All right, and we can see that we've got 80 lines going. And here we're just going through, and we can check to see if we have identical objects going on. And we can see that no, we don't. Things that don't match up because I did my subsetting. Here we can see where they do match, and here we can see when they do not. All right, so now we've already tasted polygons a little bit, but let's go a little bit deeper. So now we want to talk about individual polygons and spatial polygons. All right, so a polygon is just like a polygon. Polygons is a collection of polygons. And now spatial polygons, this is a class to hold polygon topology without attributes. So this is not what I want to use if I have data to connect to regions. So here, if I look at the polygon class, we see that we have label points, we have area, we have any holes. Is this region a hole? Yes or no. ring direction, so the direction of plotting, and coordinates. And this is an extension of a line. If I look at polygons, we can see that we have a list of polygons. So then we have a plot order for each of those polygons. We have a label point, we have an ID to keep things organized, and we have the area of each polygon. And so this does similar work of creating spatial polygons, which are a little bit more specified for spatial data analysis and regular polygons. And we can see that if I take a look at it, of the output from a spatial polygons, we have our bounding box and we have our projection string. And if I want to go deeper into this, and this gets to be important when I start pulling in data into situations, the plot order, I just take that slot and I can see this is the order by which things are being plotted. And if I want to, I can permute this around. I avoid not changing the order of things if you can avoid it. One thing I could do is I could rearrange the order by the area, but this is just demonstrating that we can do it, really is the point of this. All right, so let's keep on going. This turned out to be a longer video. So now let's do an example involving states. So I'm using the maps package, maps function to say, hey, grab states, don't plot it, but I do want it to be filled in if I'm working with it. And here I'm going to take the state names, and things are not exactly the way we would normally want it. I've got a colon and some information I don't want. I just want state names. What this is doing is that this is splitting off the part I don't want. And now we want to take a map and we want to convert that map to spatial polygons. So I specify the map, which I said up here. Now for the IDs, I just take the names, which I extracted from the map a moment ago, and then I'm manually specifying the projection. Now here is some data. So what this did, this converted the map to spatial polygons for me. And here this is reading in data connected to each state. And so let's take a look at what doesn't match up in my data set. So here, if I was to actually look at my data set, I would have in here, I have the continental United States, and I have, sorry. Yeah, so we have Alaska, we have Hawaii, we have the United States. This map does not include overall United States, does not include Alaska and Hawaii. And if I want to, I can specify this very nicely. And so this way I'm limiting to just where I have the matching if I want to start putting things together inside a spatial polygons data frame. So now we'll take a look at spatial polygons data frame. All right, so what's going to happen here is that I'm going to have spatial polygons and I'm going to have a data frame. So here I have regions on the Earth. Here I have data connected to each region. So this could be, let's say, each county in the United States, and I could have the number of COVID cases or the population, average age, things like that in a data frame connecting to the region. All right, and here's my data frame. Here, and I've got an abbreviated name, V-score, M-score, and then PC. And if I take my spatial polygons data frame for each of the states, I can see that I've got a data here. I've got my polygons, my plot order, my bounding box, and projection string. So this is very similar to a spatial polygon, but now I have a data slot, and the data connects to each individual region. And you'll notice that if I change up a row name, I'm changing an ID. And you'll notice that everything was lowercase previously. If I put capital A Arizona, everything's going to get messed up. So it won't even let me do it. It just says, hey, there's a problem, there's an error, get out of here. All right, so now let's start doing some subsetting just like we've done before. And so here, what we're going to do, we're going to say, hey, I don't want DC because it's not actually a state. I guess we're not talking about Guam, American Samoa, or let's see, the Puerto Rico, or the Mariana Islands either. So I can do my subsetting, put a logical vector inside there to subset my data frame, and it will automatically take care of subsetting the coordinates and subsetting the data frame for me. Very nice. And if I run a summary, it will give me a summary on the spatial polygons part and a summary on the data frame. So I get my bounding box, I get my projection string, and I get a summary on my data frame. That's very nice. All right, this next part, I couldn't find this file, so I just skip over the code. And I'm going to skip over another part later down. Now, spatial polygons. So here, this is very similar. It's a polygon topology. So this isn't like the exciting topology from a math class. This is map topology, which is kind of, technically it's topology, but it's not. It's not math thrill, not as exciting. And so if I want the spatial polygons, I can grab that from the slot. So up here, where did I put it? Oh, there we go. So this is an R data set, and the SP slot in there is a spatial polygon. See that we've got one polygon in there. Oh, sorry, there's multiple. There's one slot with multiple polygons in there, and we can see how many of these are actually holes on there. So remember, if I'm talking about something like a lake, so like Lake Okeechobee in Florida, when I plot Florida, if I want to include that that lake, that's just going to be a hole in there. And so most of the time, it's not a hole, but there are a few times it is. So it might be if there is a region like contained inside another region, like a donut hole, then that will be a hole or a lake or a similar object like that. And here the ring direction specifies the direction that the lines are plotted as we plot the boundary of the polygon. Now, RGOs gives us the option of creating comments on our spatial polygons. And so here I can print those comments. If I want to, I can go ahead and plot my spatial polygon. And we can throw on some text on there. So here I'm just getting the label point. And so we can see the points throughout. And I believe that this has to do with the plotting aspect. I think I made another map of this. And so here's another one, and this is specifying another aspect. And so we can see that these are, I believe it specifies the plotting order. So this is like third in the order, while like 0 is plotted much earlier. Now, when I talk about my grid topology, Grid topology class is a class for defining a rectangular grid of arbitrary dimensions. So something that's important about this is that this is a grid. And so things are a little bit more complicated. That here's the cell center offset, cell size, and cell dimensions, which are all numbers. So now if I want to go ahead and create my grid topology for this bounding box. So notice that what I'm doing, I'm passing a bounding box. I'm giving it a little bit of offset. So here I'm specifying the center of it. Give it a little bit of offset. Give it a little bit of, specify how big each cell needs to be. And then specify the cell dimensions. And I'm going to end up getting my topology grid. And this will specify all the features of that. Now for a spatial grid, this is a class of defining full rectangular grid of arbitrary dimensions. And so here we're going to have our grid topology, our bounding box, our projection force string. So that grid topology that we specified previously specifies the actual features of the grid. And now this specifies where it is and how I print it onto a map. And so I use the spatial grid function, which is in the SP package. I forgot to put that on. And that specifies the object for me. And we can see what's going on. We get, our bounding box, and we get the features of our grid topology. Now we can also look at spatial grid data frame. So after I have my grid, I can specify points onto there. All right, so if I want to connect to each point on my grid, I can take data and connect it using a spatial grid data frame. Now here, if you take the author's code, the author goes ahead and takes a data set that's on the website, converts it over, and then saves it to a format that is useful. So here, the author loads a particular format, saves it, and then loads it. And I'm just following the author's code on this. And then goes through and specifies when we have missing. So if I have a spatial grid data frame, band 1, if it's less than or equal to 0, I want everything to be converted to a missing value. Now, this code, I couldn't get the data set previously. I mentioned that in the video. So I'm just presenting it in case you find the data, but I couldn't find it. I'm not worried about it. So let's take a look at the class of my spatial grid data frame. And of course, it's a spatial grid data frame. And we can look at the grid slot. So here I've got that grid going nicely. We can look at my B box. And once again, we see it. Now notice I never specified longitude and latitude. So it's just assuming that it's going to be X and Y and letting me figure out the coordinates in case I want to do something other than longitude and latitude. Here, object size tells me the memory size of the object. Here I can see that this shows me that almost all of the memory is coming from the data aspect, not the grid itself. And we can run summary on our data frame. And we can convert this to a spatial pixels data frame. So here, this is specifying things in terms of pixels this time. But everything pretty much works out the same thing. I'm going to have a grid of pixels, and I'm going to have a data frame, and then they connect. And here, we're just kind of digging into individual things. Like we can see how if I use the prod function for product, I can see how big my spatial pixels are. And so for spatial pixel data frame, once again, I can just work with it like I have with everything else so far in this video, is that I have the spatial aspects of what's going on. Here I do have a grid going on for my pixels, so that's included here, but I also have a data frame connected to each of those points on the grid. And look at the size. We can also just have individual spatial points and individual spatial pixels. So here, if it's spatial points, it's going to be, and we looked at this previously, class for is regularly spaced points, while spatial pixels is class for defining a pixel, possibly incomplete rectangular grid of arbitrary dimensions. And everything works similar to what we've got thus far. And this is pretty much just repeating the other examples. Now, a raster layer, this is important if you're going to be doing spatial data analysis. A raster is a database organized as a rectangular grid that is subdivided into rectangular cells of equal area in terms of units of coordinate reference system. The raster package defines a number of S4 classes to manipulate such data. Most of the time, most uses, this is going to be basically a picture that is connected to coordinates. So usually when I look at a raster, it's going to be a picture, so like an aerial map, a satellite map, or maybe a map such as like a Google map connected to latitude and longitude. And there's some slick things that the raster package does in terms of memory to keep things manageable. And so we can see that I've loaded this, but it's not actually in memory. That way I don't choke out my machine. I'm only going to call things when I actually use it, when I'm actually going to engage with it. If I want to get cell stats, I can do that to get minimum. Now, something that's interesting is I can take a raster layer object and I can put it in the raster function and work with it again. And we do this so that I have additional options in manipulating my raster object, my raster layer object. And so we can get like our block size, and we can work with writing, and so that we can record what we've got. We can do a for loop across each individual block. And so here, if I just want to plot everything, there we go. And I use the data to get the colors here, so that way it pops. I get more to work with. All right, well, that's all I've got for you. Take care and goodbye.